In this presentation, we're going to talk about composites. And we're going to cover some of the definitions of the terms used to talk about composites, the history of composites, matrices, fibers, and the application of composites. The definition of a composite material is an engineered material made from two or more materials with significantly different physical or chemical properties and which remain separate and distinct on a macroscopic level within the finished structure. So adobe bricks or clay and straw bricks are a good example of this. They use two components, clay and straw. They're mixed together with water, and then they're put into a form and they harden and dry and become one solid brick. If you were to cut the brick in half, you'd see that the straw is still there and that the clay is also still there, bonding the straw together. So that is a very basic, natural form of a composite material. Concrete and plywood are also composites. Concrete or reinforced concrete has rebar that runs through it, and then the concrete is poured over the rebar and sets, much like the clay and straw bricks. The reinforced concrete uses the concrete for its compressive strength and the steel for its tensile strength, and as a result, the reinforced concrete has the best properties of both materials. Plywood is another example of a composite. It's made up of thin layers of wood and glue, and the wood is strong in one direction but not in the other. So the grain of the wood imparts strength in one direction in the wood but not in the other direction. So in this case, they engineer the plywood so that the strength of the wood runs at 90 degrees of to each other in the plywood in each layer, and that way you have strength in all directions. So a piece of plywood is stronger than a piece of regular wood of the same dimensions. Fiberglass is also a composite. It's a modern one where the resin is used to impregnate the fiberglass fibers. It's used on airplanes, bathtubs, cars, lots and lots of different applications. It's nice because it can form complicated shapes, and it's easily formed. Carbon fiber is similar to fiberglass. It's just stronger, has better tensile strength. It's known for its lightweight characteristics and its high strength to weight ratio. It's also a very rigid material and is used in all kinds of industry today. The matrix is an important part of the composite. It's the resin or the glue that binds together the fibers. So in the clay and straw bricks, the clay would be the matrix of the composite. In this picture down here, there's a rod, a composite rod made from carbon fiber and a matrix. The black dots represent the carbon fiber fibers, and the gray represents the resin matrix. The ability of the resin to bond to the fiber is very important. So the matrix has to bond to the fibers. Yeah, and that's going to greatly affect the strength of the composite. The better it can bond and the stronger the matrix is, the more strength your composite will have. There's many different fibers you can use to make a composite. There's natural fibers like vegetable, wood, and animal fibers. We can place sawdust into a resin, and that'll give it different characteristics. You can use fibers from plants or wool from animals. So those are natural fibers that you can place into composites. Some synthetic fibers are your mineral fibers like fiberglass, carbon fiber, and metal. If you look at the fiberglass, you can see it's just little strings of glass, so very thin little ropes of glass, and they're very smooth and not a lot of area to grab onto and really bond the resin to. So they don't really bond to the resin very well, as compared with this piece of carbon fiber down here, which is very rough, and it bonds to the resin much better, has nooks and crannies for all the resins to get into and bond with. So this is in part why carbon fiber has such good strength and rigidity in the final composite. There are also polymer fibers we can use, like Kevlar, polyester, and nylon. You can see that these are also very smooth fibers, so they don't bond real well to the resins either. But they may have other attributes that you'd like to have in your composite. So maybe you'd like a more flexible composite or one that's very durable. Kevlar has the ability to resist cutting and also to be resist abrasion. So if you're going to have a surface that's going to go under a lot of wear, Kevlar might be a good fiber to put inside the composite to resist wear. So how are we going to maximize the strength of our composites? First, we're going to make sure the matrix is going to bond well to the fibers. So some materials or some matrices or resins bond well to some type of fibers and some don't. Polyester resin and fiberglass bond pretty well together, but epoxyacryl or vinyl ester resins and fiberglass really don't bond that well together. Carbon fiber and acrylic resins bond very strongly together, so that would be a good choice. The matrix needs to be strong as possible, so the better the matrix is, the stronger the composite's going to be. The matrix to fiber ratio needs to be as low as possible, so the more matrix you have, the less matrix you have and the more fibers you have, the stronger your final composite's going to be. Of course, the resin or the matrix needs to be as high quality as possible, and then the fibers need to be as strong as possible, and that is also could be as long as possible. If we have nice long fibers in our composite, that's going to add more strength as opposed to short chopped fibers. Pre-stressing is something that some industries do before they bond the matrix to the fibers, and basically that's just pulling the fibers tight so that before you bond them, so while they're in the resin and the resin hardens around them, it's going to harden in a pre-stressed type of condition, and that'll allow for more rigidity and more stiffness to the matrix. We don't do that a lot in prosthetics and orthotics because of the odd shapes that we work around. It's just not something that's typically done. So now we're going to talk about the different forming methods to make a composite. And the first one's going to be open molding. And when you do open molding, it's just like it says, it's open to the air. So this fellow over here is doing open molding and a hand layup on a inside of a ship, it looks like. So he's laying in the fiberglass, wetting it with resin, then rolling it by hand in, probably using a squeegee and a roller to try to work the air out from between the layers. So this is a very manual process, just mechanical resin application. The next one's a chop laminate process, and this uses a gun that spits out the matrix or resin, and then also chops up strands of fiberglass into little pieces at the same time and sprays it into an open mold. It's very fast, very efficient. It's used for making a lot of things like bathtubs. Some kit cars and things are made out of this process. It's a random orientation of the fibers, so you have good strength in all directions. And it's fairly cheap way to apply the composite material to the form. And then on the bottom we have filament winding. This is kind of an unusual one. It's mostly used for making tanks and like high pressure tanks and things like that. But it basically has a spool that spins, and then it feeds out the carbon fiber braid or weave onto it, and it moves back and forth and just wraps the whole thing in carbon fiber. And this applies tension to it, so it's applying, molding this tank under tension, which is going to give it greater strength and greater rigidity. Then we have closed molding. This is when the mold is sealed from the outside air. And the first one is compression molding. We typically don't do this in our industry to make sockets and things in the office. It is, however, used in other parts of our industry. And basically it's a wet layup process, so the fibers are impregnated with the resin or the matrix before the forming happens. So they'll lay this in here, they'll have it soaked in the resin, and then they'll have these two big dies that come down and exert a lot of pressure and maybe some heat to cause the curing of the resin. And after it cures, then they'll open it back up again and pull out the finished part. So that's compression molding. The dies are very expensive to make, so for most of our work is custom, so it would be too expensive to make this for each individual patient. So this is done more for mass production, where you're trying to make a few thousand of a part. And then we have vacuum bag molding. Basically it's a wet layup technique, so we're going to saturate all the fibers, wet them all out, and then put a membrane of plastic or PVA material over the top of them, seal it off, and then apply vacuum. This is also how you do pre-preg, and that stands for pre-impregnated fabrics. These are fabrics that come with the resin already in them. You just lay them down into the mold, place a vacuum bag over them, apply vacuum, and either cure the resin with heat or UV light or something along those lines. So that's a pre-preg type of material done by vacuum bag molding. It's important to notice that the vacuum is applied after the resin is impregnated into the fiber. The next process is vacuum infusion, and the difference between this and the wet layup vacuum bag molding is that everything is laid up dry. The membrane is then put over the top of it. Vacuum is applied, which pulls all the air out of the fibers, and then the resin is placed into the fibers and infused by vacuum into the fibers. This removes a lot of air bubbles and gives you a little bit more of a solid lamination. And this is the process which we use in the O&P field for most of our socket production. So vacuum infusion is one of the more popular methods in orthotics and prosthetics. And then we have continuous lamination down here. This is a machine that just puts out a sheet of some type of composite. So it basically just makes a long roll of some type of a composite material that continuously puts out product, and then a cutter cuts it off into panels. So it's similar sort of to an extrusion process where it's just a continuous process and doesn't stop. So in prosthetic forming, how do we form our sockets and our devices when we go to laminate them with composites? The first thing is vacuum infusion. So it's a dry layup process, and then we're going to infuse it with resin under vacuum, and we're going to have high control of our fiber orientation. So we're orienting our fibers in this model. We can choose exactly where they're going to be because we're going to hand lay them up, and we can make areas strong or certain areas a little bit weaker or reinforce what we need to. So when you do this type of vacuum forming, you have a very good control over your fiber orientation and the strength of the finished prosthesis. So that's vacuum infusion. The next one is vacuum bag forming. This is a wet layup technique, so the fibers are going to be pre-impregnated with some type of matrix or resin, and we're going to place that into a vacuum bag, and then we're going to cure it. Sometimes this is in the oven. This fellow here is getting ready to place this in the oven, so has his layups here of the different carbon, looks like pre-preg materials. He's going to pull a bag over the top of this that's heat resistant, apply vacuum to it, and then place it in the oven until the resin cures. And again, we have high control of fiber orientation with this also because we can place the fibers wherever we would like them to be in the orthosis. The compression molding we use in prosthetics, but it's more a manufacturer's technique. It's going to have expensive dies. It's going to have a real high fiber to resin ratio. So that means that these are going to be really strong because we're able to compress them and squeeze all that resin out and just leave the fiber and a little bit of resin behind, and that's going to make a nice strong carbon fiber structure. It's always a wet layup. If you look at this fellow over here, he's running on some flex feet, and these are made by a compression molding die type technique. Very strong, very lightweight. Now I'm going to go over some of the some examples of the different fibers that we can use. The first one that's used commonly is what's called nylon stockinette. So you can see it's tubular. It comes in a large roll in a box like this. You can cut off as much as you need. Nylon is not extremely strong, but it makes a good durable socket. For years, we just used simply nylon for all our sockets. They worked well. They were a little more flexible than they are today. And they tended to crack after a few years of use. So they just weren't as strong as the materials we have today, but it can work for a socket if you want a little bit more of a flexible socket. So that's a nylon stockinette. They also make a nylon stockinette called Nyglass, and this material is made out of nylon, but then it has little pieces of fiberglass intermixed with the weave, and that gives a little bit more strength and rigidity to your socket. The next type we have here is fiberglass, and this is a sheet fiberglass, so it's just like a sheet, one flat sheet. It has a weave that goes 90 degrees to each other, so we have half the fibers running this way and half the fibers running that way, and that gives us good strength in both directions. So it's a nice weave for overall strength, and that's fiberglass in a sheet form. All these things can come in different materials. So like you can have a sheet, or you can have tape like this here. This is tape, and it's carbon tape. This could also be fiberglass tape if it was made out of fiberglass. And if you look at this, the difference between this one and this one of the weave, let's see if I can get a close-up of that. And then we'll also do the braid here. So this is braid, and this is a tubular material. So you can see it's a tube. It opens up like that, and it stretches a lot, so it can go around to odd shapes. When you stretch this out over the top of your model, you don't want it extremely stretched out as big as it can go. You'd like it to be kind of halfway in the middle, kind of in a relaxed state, with these the weave of the fabric going at about 90 degrees. So that's about when it's its strongest, about like that. So I'll just kind of lay these down here, and we'll kind of look at the different weaves, the different fabrics. Let's see if I can zoom in on these. So if you look at this weave here, this one here is at 90 degrees to each other, just about. So 50% of the fibers are going this way, and 50% of the fibers are going that way. If you look at this piece of carbon, let me back out just a hair. All the carbon fiber is running in this direction, so it's 100% of the carbon fibers are going long ways on the tape. And there's just little white threads of fiberglass in here, and those aren't really for strength. Those are just to hold the tape together while you're laying it up. This one here really only has strength in one direction, so this piece of tape's only going to have strength really in this direction. If we tried to lay it up and we wanted strength across this way, it's not going to be very good for that. So this one here is going to give you strengths in multiple directions, because 50% of the fiber is going in this way and 50% is going this way. This one's going to give you strength just in one direction. And this here is the braid. And if you look at this one, it's manufactured with a weave like this, and as you stretch it, the weave flattens out. Try to back up a bit. The weave flattens out, and then as you compress it back together again and make the tube smaller, it kind of creates more of a acute angle here, and the fibers run more up and down than side to side. So when you laminate with this, you'd like to have these fibers at about 90 degrees to each other, so about like that, and that'll give the best overall strength for the prosthesis. These are some examples of finished AFOs and some sockets here I'm going to show you. So this is a AFO that's been made out of carbon fiber. If you look at this, you can see the carbon fiber running through it, and you can see this weave is running 50% this way and 50% that way. So it's kind of a all-around strength type of a weave. So you have strength in both directions, and there's areas that have been reinforced with extra carbon fiber. So there's an extra piece of carbon fiber here, a little bit more carbon fiber here, and less fiber up here. So we've got spot reinforcement, so we've controlled the strength of the layup by adding and reducing the number of layers while we were laying it up. So this is a good example of how you can vary the strength and the orientation of your fibers. Now this was a pre-preg type of a material where it came pre-impregnated, we heated it up, and then went through a consolidation process in the oven. So that's a carbon fiber AFO used with pre-preg material. And then this is a cutaway of a prosthetic socket. You can see the texture of the nylon stockinette that was used in the layup, and the dark flesh tones are the matrix or the resin. So we have two distinct type of materials here. If I turn it over on edge and we look at the edge of it, if I can zoom in on that. You can also see that there's a better shot of this here. There's right in here you can see there's resin, and then there's the nylon inside of here. And since this is pretty much all nylon lamination, there may be just a little bit of niglass in here. This is going to remain somewhat flexible and not as rigid as the carbon fiber. So if I take this and bend this, I can actually flex this socket, because the nylon, one of its characteristics is it has a little bit of flexibility and give to it as compared to carbon fiber. So if you want a socket that's flexible, you can use nylon to give a little bit of flexibility to the socket as compared to carbon fiber. Those are just a few examples of composites. You'll learn a lot more about them as you go through the class. And if you have any questions about this presentation, feel free to ask one of your instructors.